Welcome. We're going to be doing Physics 123, lab number 4. This is Energy Conservation Work and Internal Energy, or the Specific Heat Lab. Today we're going to be looking at this aluminum block, and we're going to be putting work into it by cranking this. And it's hanging from a mast, and so we have a leather strap. This is creating friction, and from this friction that we're adding by work, we're going to examine the internal energy change of this aluminum block. Okay, so how we're going to measure the temperature of this aluminum block is if you come in here, we can see inside the block this little component, which is deep inside of it. That's called a thermistor. And so this thermistor changes resistance based on the temperature. And so these little wires here actually go through into the crank and out to these leads, which are connected to an ohm meter. So this is measuring resistance in ohms, okay? And actually, it's measuring the resistance in kilo ohms. And based on this resistance, we can find the temperature. And so we have a resistance to temperature conversion chart right here. And so for any resistance that we measure, we can find its value and then look and see the temperature in Celsius. And so that's how we're going to find the temperature. We can also cool down the cylinder in the freezer. Here we have these steel blocks, and we just stick it on the end like this, and then this will cool down the cylinder. And then if we want to heat it back up, all we have to do is crank it. So we just have a crank here, and this is just moving the cylinder. And as we have this leather strap, we have friction, which is putting heat into the cylinder. And this leather strap is hanging from the leather strap is a 1 kilogram mass. Okay, we're going to go ahead and start with our experiment here. So the first thing that we're going to want to note is the room temperature. And so this is the reading on our our ohm meter. It's 3.37 kilo ohms. And so if we come over here to the chart, 3.37 corresponds to, looks like 22.5 or 22.6. So somewhere in that range, which is what we'd expect from temperature. And so what we want to do is, let me grab the cooling thing. We're going to take this out of the fridge, and we're going to go ahead and cool it. And why we're cooling it is because we're going to be cranking this and putting in some work. But if this is at a different temperature than the room, there's just going to be natural heat flow from the cylinder to the air. And so what we want to do is we want to cool it so that when we're cranking it, about half the time is spent below room temperature and half the time is spent above room temperature. And this way, the heat, as it's leaving to the room, kind of cancels out on both sides. And so that way we can just only look at the change of internal energy due to the work that we put in. And so if we're at, so we're at about 22 degrees, and we want to go, when we crank 100 times, it's going to be about 10 degree change. And so I think in your sheet it says to start around 18. I think I'm going to start around 17, so that we're 5 degrees on each side. So let's go ahead and see where we're at right now. 3.74 corresponds to 20. Okay, so that cooled at about 2 degrees. I'm going to go ahead and cool it a little bit longer. Once we get down to the correct temperature, you're just going to want to write down the room temperature. You're not going to use that for any of your calculations, just to verify that the room temperature is about midway between the start and end temperature. So actually should have already written that down. But once we get to the correct temperature, you just write down the start, and then I'll crank it 100 times. And when I'm cranking it, every revolution here is 12 times, because there's some gears in here that cause the actual cylinder to rotate in its leather strap 12 times for every one revolution. So I'm doing one revolution with the handle, that's 12 revolutions here. 100 revolutions with the handle would be 1,200 revolutions of the small aluminum thing that we're actually examining. Okay, let's check this out here. 3.93. Come here, 3.93. Okay, we're getting down to 19. I'm going to go ahead and try to find a colder one of these actually. I'm just going to hold it here, and we'll come back when it's down to the correct temperature. Okay, and I think we're at the right temperature. Let's look at the resistance reading. So we're at 4.22. It's warming up, but let's call 4.21 actually. 4.21. It's right here. Let's go 4.2 because it's already warmed up a little bit. So we're at 17.2 is our starting temperature. I'm going to go ahead and crank it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 93, 94, 95, 96, 97, 98, 99, 100. So that's this is the resistance. 2.75 we'll call it. And then we come over here, 2.75 right here, 27.8. So we went from about 17 to 27, which is 10 degrees, which is what we expected. And so from those, the initial temperature to the final temperature, you can compute the change in internal energy of the aluminum and then compare that with how much work we put in. Those numbers should be pretty similar. They may not match up exactly because, like I said, there's some effect due to heat flow to the room, but they should be pretty close. And so good luck with the rest of your lab. That's all the data that you need.